Seeing a nucleus is very hard. Bouncing alpha particles off them allows us to see it to a certain extent, but alpha particles are very big in the grand scheme of things. If we want to see a nucleus more clearly, we need a smaller particle to throw at it. For this reason, we use electrons. The problem with electrons is that they have a negative charge. The nucleus has a positive charge, so if you fire an electron at a nucleus slow enough, it will stick. The answer is to fire the electron at the nucleus faster. Actually, that's not really true. No matter how hard you fire an electron at a nucleus, it will always be attracted to it. You cannot, therefore, try to measure the size of a nucleus by firing electrons at it and measuring the angle they bounce off at. Instead, you need to use a different property of electrons. Their wave properties. Wave-particle duality says that particles have wave properties, and waves have particle properties. Actually, the concept goes a lot deeper than that, but we can still use the concept to our advantage. De Broglie gave us a method of expressing a particle's properties as wave properties. De Broglie says that the wavelength of a particle is equal to Planck's constant divided by the momentum of that particle. Force is change in momentum over time, and energy is force times distance, so energy is momentum over time times distance. Distance over time is velocity, so energy is momentum times velocity. Rearrange that, and you get momentum equals energy divided by velocity. Put that in de Broglie, and you can express wavelength as energy as well as momentum. The wavelength of a particle is equal to Planck's constant divided by momentum, or speed of the particle, times Planck's constant divided by the energy of the electron. If we say that the electron is travelling at the speed of light, we can give the wavelength as a function of the energy of the electron. For an electron of 5 megaelectron volts, the wavelength of the de Broglie wave would be 2.5 by 10 to the minus 13 meters. Okay, so we have been able to give the electron a wavelength, but how does this help? If we fire an electron at a nucleus, it will be attracted towards it, so we can't use Rutherford's method to calculate its maximum possible radius. Instead, we use a completely wave-based approach. We fire loads of electrons at the gold nucleus. Instead of treating the electrons as particles, we treat them as a light source. Instead of bouncing electrons at gold leaf, we shine the electrons at it and look at the diffraction pattern they produce. If we measure the angle from the normal to the first maxima of the interference pattern, we can use diffraction theory. Sine theta, the angle we measured, is equal to 1.22 times lambda, the wavelength of the electron from before, divided by the diameter of the nucleus, to work out the diameter of the nucleus of the gold atom we have shone our light on. Half the diameter equals a radius, so we have a value of the radius of our gold nucleus. By comparing the nuclear radii using this method of the nuclear number of different isotopes and elements, we can show that the radius of any nucleus is equal to the cube root of its nuclear number times by the nuclear radius of a hydrogen nucleus, which is about 10 to the power minus 15 meters.